talk about some work we've been doing in the past couple of years on quantum groups and lower dimensional gravity models. So let me start with the introduction. So symmetries are of course very important to understand exact solutions of dynamical systems. And in most cases, these are linear, so just Lie group symmetries, but sometimes nonlinear symmetries emerge in models, quantum group symmetries, and they can be equally important to understand various aspects of the system that we want to understand. And the goal of my talk today will be to discuss two applications of the emergence of quantum groups and quantum group symmetries in lower dimensional gravity models, and partially motivated as a guide towards going beyond the usual asymptotically ADS boundary conditions. And I will discuss two different applications, one of them in 2D gravity, and in particular I will discuss Q deformation, a quantum deformation of the usual holographic dictionary, and I will embed this in a specific model of 2D quantum gravity called Liouville gravity. And this was done in this paper that appeared last year on Archive with Andreas and Jacopo, who are both here and can answer more questions if you're interested. Andreas also has a poster here on this. And my second application, which is a completely independent application, so my talk essentially has two parts that are not connected to each other, will be about 3D gravity, and I will discuss a minimal factorization map. So I want to factorize the Hilbert space of 3D gravity in, let's say, left and right parts. And I will do that in the Chern-Simons formulation of 3D gravity and discuss some of its implications. And this is based on also a paper that appeared last year with my PhD student, Xifeng Wu. Okay, so let's start with the first part, the 2D gravity part, and I want to think about the boundary of the 2D gravity, which is a one-dimensional boundary. And if you just think about the two-point function in a one-dimensional conformal field theory, then, as also in a chiral two-dimensional CFT, this two-point function is fully fixed, is fully bootstrapped just by SL2R invariance, by being SL2R invariant. So if I write the three generators of SL2R in this way, so E minus, H, and E plus, and as these first-order differential operators, they satisfy the SL2R algebra. My boundary carries this coordinate Z, and then delta is the conformal weight. And then, as in textbook CFT calculations, if you look at the CFT two-point function and you demand that this is invariant under these three generators, so this leads to three ward identities, which you can uniquely solve up to an overall prefactor, the overall normalization, and it just leads to the conformal answer, of course. Now, holographically, this is interesting because, of course, this SL2R invariance encodes the bulk ADS2 isometries, and you can view this as one of the main indications of holography. So this is the standard story. And now I will be interested in trying to find a deformation of this setup. So I'll try to mimic these steps here to get to a Q deformation, so a very specific type of deformation mathematically. And the way to do that is to realize that the above representation of these three generators in math is just the principal series irreducible representation of SL2R. So if you just look at the math textbooks, let's look at the principal series irreducible representations of the Q deformation of SL2R, of SLQ2R, and try to play the same game again. So here are the three generators that you can find in the literature. So again, E minus, E plus, and H. The H is the same, but you can see that the E minus and the E plus have changed a bit. They look more complicated. There's this function here, this RQ squared. What RQ squared does is it scales a function. So if it acts on a function, it changes the argument by, well, the subscript times the argument. So you can see that this thing is like a discretized version of a first-order derivative. So if I take the limit where Q goes to 1, so Q to 1 will be the undeformed limit where I go back to the normal SL2R. You see that I'm just reproducing the definition of the derivative here. And the same thing for E plus. So this is some sort of discretization, if you want, of the derivative. And this is mathematically called a Q deformation. So these are the three generators. Now again, I want to play the same game. I look at my two-point function that I want to bootstrap with this technique. So O of Z1, O of Z2, and now I demand that it is invariant under the action of these three generators, and this again leads to three ward identities, Q ward identities if you want, and I've written them down here explicitly. And now the task is solve these to find your answer of your two-point function, but now constrained with this Q deformation of SL2R. Now the solution itself will depend on the specific range of Q, so I haven't specified at all what Q is. A priori Q could have been just an arbitrary complex number. But the answer is unique up to a choice of normalization. I'm just going to show it to you here. Now, there's two particular ranges of Q in the complex plane that are interesting in terms of quantum groups. One of them is where Q is on the unit circle, so the modulus of Q is 1, so I can parameterize Q as a phase, as e to the pi I b squared, where b squared is a real number then. And then you can solve these equations and you find this answer. So the SB function, so I won't bother you with the technical definition of what this thing is. This is just some sort of deformed version of the gamma function, if you want. So this is the answer you would find, and you can show that if Q goes to 1, we get back to the normal SL2R standard CFT answer.
Sorry, Thomas, are you going to say why you're interested in this type of deformation?
Well, because I want to look at a deformation of holography, if you want. So that's my motivation,
Yeah.
and for the moment I'm just playing a symmetry game.
Okay.
This is just the symmetries. In a couple of slides I will try to find the structure concretely in a model.
But why these Q deformations in particular? Why?
At the moment it's just because it's an interesting symmetry mathematically and I want to see where this leads to. But physically, I want to back away from the usual ADS CFT, the boundary, I want to change it, I want to study different forms of holography, and it's an interesting question whether one can Q deform a holographic dictionary. But I will show you that we can actually get this answer from an actual model. So it's not just a purely formal game then.
And are those unitary representations?
This
For any,
yes, these principal series.
There are
Yes.
some range of delta of this.
Sorry, these principal series representations are
yeah,
unitary
for
representations.
any range of delta.
Well, there is no, well. Is it, yeah. Is it delta the J? Do you remember? Okay, so J is like minus a half plus IS in the SL2R case. But then Q over 2 plus I times something in the, yes. Okay, but let's continue now. So that was the answer for Q on the unit circle. Now there's another interesting range, which is when Q is a real number between 0 and 1. That's not the case that I will study here, but this has been studied in the past in terms of trying to find the deformation of worldsheet string theory a long time ago, and more recently by Almiri and Popov in terms of the quantum hyperbolic disk. In that case, they also find an answer like that in terms of what are called Q-Pochhammer symbols. I won't go in that direction, but just to let you know that there is an analogous story here for Q in a different way. I want to focus on the case where Q is on the unit circle. Now, given this bootstrap boundary two-point function, there's a lot more that you can say about this. So, just as in the case of the normal hyperbolic disk, this is a z coordinate here that I use to parameterize my boundary. You can view that as just the holomorphic coordinate of a coordinate pair, z and z star, that I define in the bulk, and then I define my boundary circle to be at z times z star is 1, so just the unit circle. Now, with this deformed structure, there's actually quite a few properties that you can show. First of all, well, by consistency with the quantum group code product structure, which I haven't specified, but the quantum group comes with a lot of extra structure. And with this structure, you can actually show that the action of these three generators, HE plus and E minus, also on the conjugate coordinate is fully fixed by consistency. And moreover, that the Z coordinate and this Z star coordinate that I use to parameterize my bulk, they must be non-commutative, and they must be non-commutative in this specific way. And you can fully get this relation just from the structure of the boundary and this quantum group symmetry structure. Now, a 2D space parameterized by this non-commutative structure is a known space, so it's a 2D non-commutative space-time, and it's called the quantum hyperbolic disk. So the reason that I mention these things is that you can actually just deduce this bulk, Q hyperbolic disk, from the boundary. So if we, in some model, which I will show you in a couple of slides, find this boundary correlator somewhere, we have this bulk structure coming with it automatically. So this is sort of implied by this boundary structure. Just to get some intuition into this non-commutative coordinate, there's a suggestive choice of coordinates you can make. Instead of the Z and Z star coordinates, I can transfer to a radial coordinate that I call R, and an angular coordinate that I call phi. And then this non-commutativity relation, it actually just boils down to the commutator of phi and r being non-zero. So the intuition you would have, and that's the picture that I've drawn here, is just like in phase space Q and P, they don't commute with each other, so you have a fuzziness in phase space, or an uncertainty relation. You have the same types of structure here, but now it's fully in coordinate space. So that's why it's called a non-commutative space-time. Now, I will rewrite my answer briefly here in order, for it to be more suggestive. The first thing I will do is I will reparameterize my two-point function to get the thermal correlator. So what I've shown you earlier was just the zero temperature correlator, just generalizing the 1 over Z1 minus Z2 to 2 delta from CFT. If we want to get to the thermal answer, what we have to do is we write Z as the exponential of something, and that's what we do in ordinary CFT. So there's an analogous trick you do here to get to the thermal answer. Turns out that there's like an extra factor of Q to the 1/2 and Q to the minus 1/2 that you have to insert here to get the correct thermal transformation. This is to get the KMS condition to work out with this answer. Well, I won't bother you with more details. But then you get this thing, and here I call the difference between the angles, so phi and theta are two angles on the boundary between 0 and 2 pi, so they just label 2 points on the boundary circle. And their difference I call tau, essentially. So that's my Q-deformed thermal boundary two-point function. Now, an interesting thing you can do is you can Fourier transform it, you can get to its frequency contents. In this case, you need a technical formula called Ramanujan formula, so I've written it here, so it's just a technical identity with these SB functions. The important thing is the Fourier transformed thing itself, which is the thing I colored in blue here. And then you can try to interpret physically what this would mean for the bulk. So you have the Fourier transformed boundary two-point function. You can look at the poles, for instance, and the poles at negative imaginary value of omega. You would want to interpret these as quasi-normal modes in the bulk, so you can get this set of quasi-normal mode frequencies from this two-point function from there. We don't know what the bulk is because I've only looked at a boundary two-point function at the moment. But we get some hint at what a possible bulk dual, what kind of features it should have. Okay, so now the main part of this, this part of the talk is that for undeformed SL2R, we can embed this boundary CFT two-point function explicitly in a dynamical model, in particular in JT gravity, in a particular regime, which I can call the probe regime, where we have a small energy injection in an otherwise large semi-classical black hole. So a small probe that deforms your black hole. If you do that regime in JT gravity, you just get the standard thermal CFT two-point function. So that's a known story. Can we do something similar? Can I look at a model, look at some limits, and actually get this type of answer from it? Now these SBs, of course, they appear in lots of places in the literature, in particular in Liouville CFT they appear a lot, so that's where I will be looking. And the model that I want to look at is Liouville gravity, or the non-critical strain, where we take a matter CFT, Liouville CFT, and then the BC ghost CFT coupled together with total center charge 0. And I want to look at the boundary two-point function of this model. So I take this string theory, I put it on a disk-shaped world sheet. I put two boundary operators in this string theory here. So this O beta m, the beta m is just a label, matter label if you want, of a boundary operator. The details don't matter for the purposes of my talk. And these operators are just tachyon vertex operators in the string theory language. Now you can compute this disk amplitude exactly in Liouville gravity, and I'm going to call the time Euclidean time separation, or the length of this segment as tau, and then the complement of as beta minus tau, so the total circumference would be beta, would be the inverse temperature, and then the answer can be written exactly like this. So it's written as a double integral over two parameters S1 and S2. There's two density of states factors, rho of S1, rho of S2, which are just sinh and sinh. Two Boltzmann factors, or Hamiltonian propagation factors, and then this product of SB functions. So the plus minus here means we have to take the product of all cases, so there's a product of 4 SB functions that appears there. So this is just the exact answer. The energy variables in this terms of this S parameter are just Koch of 2 pi s. And you can show that this is a Q deformation of JT gravity. So there's a limit of this thing where Q goes to 1 or the B goes to 0, where this thing just becomes the boundary 2-point function of JT gravity. So this looks as a promising place to try to find the structure of this Q deformed 2-point function that we have earlier. Now, in order to get there, I'm going to need to take some limit, or I'm going to study this in some regime, and this will be again this probe regime. So I don't want to look at the 2-point function generically. I want to look at a specific regime where this corresponds in the bulk to a large black hole being slightly perturbed by a small energy probe that is injected and extracted from the system. And in order to implement this regime, or this limit that I'm interested in, I'm going to change variables. So I had my two energy variables on my previous slide in terms of S1 and S2, my integration variables. I'm going to call one of them, well, E, the energy, and then the other I'm going to call it E plus, omega over B squared. And I'm going to be interested in the regime where E will be large and this omega over B squared will be small. So large energies but small energy differences. So a large black hole and then a small energy probe, so it injects and extracts a small energy. Now this is just a change of variables, I haven't done anything, but I can write my amplitude then in terms of, instead of S1 and S2 integrals, in terms of this E and omega integral, and then I have some amplitude that I haven't written out explicitly, but it's the one from the previous slide with the change of variables. Now my probe regime, as I mentioned, will be to take E large and this omega over B squared to be much less than E. That will be the regime, the window of energies in which I'm interested in to try to find this structure. Again, my motivation is, this is just how it works in JT gravity as well. This is where you actually find the standard CFT 2-point function hidden in JT gravity. So I want to look at a very similar regime, but now for this Liouville gravity model instead. Secondly, there's also a restriction on the beta m label. So that was the label of the matter operators we have. If you want, this is the mass of the probe that we're sending in. And there is a condition that you can find just by doing the calculation. I won't go into the details here, but this is just such that the probe itself does not deform the saddle of my original, the saddle of my thermal partition function, essentially. So my energy versus temperature relation. It's a probe. We don't want it to actually deform the system in that way. Now, if you implement these two inequalities, if you look at this regime, you find that amplitude in the frequency domain looks like that. And that is actually exactly the frequency version of this boundary 2-point function we had earlier on this Q hyperbolic disk. It was exactly the same answer. If you identify the parameters like this, so this beta m that we introduced in the Liouville language is related to delta, the conformal weight we had where we bootstrapped the Q deformed 2-point function as just b times delta. So we have found this frequency domain version of the quantum hyperbolic disk hidden in this regime of our Liouville gravity calculation. So just to summarize again, so I have my two energies here in my double integral, my boundary 2-point function, and it's only in this narrow region here that we actually find this quantum hyperbolic disk. So large energies and small energy differences. So both this E and this E, they're roughly equal, but they're large. So I'm focusing on this small window here, the energy domain. Okay, now one comment here is that since this probe regime, it works at large energies, at high energies, due to the usual UV-IR correspondence we have in holography, which still holds in this case, in this Q-deformed case. This will be close to the boundary of my disk. So I can draw a summarizing picture of the situation that we are being led to. So here again I have my disk region and the blue circle is my boundary. And then is my holographic screen as well. And then at the generic point in the middle we just have the full quantum gravity, the full Liouville gravity. But as we get closer to the boundary, that's where we use this probe approximation, because this is high energies closer to the boundary. That's where full quantum gravity seems to reduce to just this quantum hyperbolic disk. So this quantum hyperbolic disk answer, or this Q-deformed 2-point function, it's still quantum, it's not classical, but it contains or less of the full quantum gravity effects, let's say, that are hidden deeper in the bulk. So the structure reduces to just a structure of Q deformed SL2R. And that's the picture we were being led to.
Can I ask a question? Is there no issue defining the boundary for a non-commutative space?
Sorry?
Is there no issue to define the boundary for a non-commutative space?
No, so there were these two coordinates that I introduced, Z and Z star, and they're non-commutative in the bulk, but they're commutative on the boundary. So the boundary is a normal, well-defined region. The boundary itself is just a 1D thing, so there's actually nothing else it can, there's no other coordinate it could not commute with.
Yeah, but if I try to define, say, a curve,
Yes.
in general it will not work, right?
Yes, you worry that it might conflict with the non-commutativity relation, right? But that's fine. So if I set Z star, so I have the formula here. If I set Z star equals 1, it implies that Z star Z is 1, so Z and Z star commute, and this relation is identically satisfied.
Okay. But
It's
if
true
I
that you
want
have to watch out for generic curves, but this relation works with having the boundary at Z star equals 1.
Normally we need the cutoff, like we don't want to be exactly at 1, but a bit away from it to the cutoff.
To like an epsilon or something?
Yeah.
Okay, sure, it does. I don't know how that would work in this case. So this is just if you want the basic thing of a Q-deformed version of holography. We have a boundary. We have a boundary two-point function which exhibits the quantum group isometries or symmetries there, and we can see it from a dynamical model. We don't have a fully worked out holographic dictionary where we can do all the same things as you can do in normal ADS-CFT. But the structure seems to be there, and that's the main point.
Can I ask something?
Yes.
So usually this non-commutativity, you can explain it with this very Cyber-written, so when there is a B field, do you have that? Can you do this interpretation here?
I'm not aware of it.
Okay, I can.
I know it, yeah.
So open strings.
Yes.
See
And you
this
do the
B
Calpramont field, and then, yes. Yeah, my picture is very different here. I'm not doing string theory at all. I'm trying to do 2D quantum
I
gravity.
mean, you said somewhere non-critical string.
Yes.
Blah, blah, blah.
Yes, absolutely. But yeah, maybe I should have emphasized
So
this more.
these non-critical
This-
strings should have a B field
Yes,
that goes
but-
through your non-commutative
Yes,
space.
but I'm not interpreting it the way you usually do it in string theory. So string theory would have this as a 2D world sheet, which is then embedded in a space-time, and that space-time can be non-commutative.
So what you could
Here it's
do
different.
to do Cyber-written there is you could insert a B field vertex operator
Yeah.
in the middle of this.
Yes, but it would lead to space-time non-commutativity, right? Here I'm interpreting the world sheet as a two-dimensional geometry that is that has quantum effects on it. So it's the target space doesn't exist in this case. So it's different in that sense. It's a two-dimensional non-commutative space-time that emerges from the structure.
So for
Usually
you-
the non-critical, the UV mode or whatever you want to call it, the scalar is the extra dimension.
Yes.
That's how you interpret.
Yes. But from what I remember from the Cyber-Witten story, they get non-commutativity in space-time, right? Not in.
But it doesn't matter because you, okay, after, sorry.
Okay, so right. So that's
Sorry,
the.
so you call this full quantum gravity because of non-commutativity between coordinates, or?
No, I just mean the full Liouville gravity answer, the full exact disk answer.
This,
The full exact disk answer doesn't look like a Q-deformed two-point function of CFT. But there's a regime in which it does, and I argue that it's close to this boundary. That
like for small separations?
Sorry?
For small separations?
Yes, if I do that so I use my two-point function as a probe, and I only see this region if my probe points are relatively close together, so that my I don't go too deep in the ball. That's when I get this region. Okay, so this was all for Liouville gravity. Now we have some work in progress where we try to understand if a similar story actually holds for double scale SYK, because it's structurally closely related to Liouville gravity. In particular, it has a similar bulk description. but it is more complicated due to the energy spectrum being different. The energy spectrum in that case, I haven't shown what it looks like in the usual gravity either, but in the WSK case, it has a finite support, and so it has a maximum in the energies, but then this makes this probe regime a little bit more confusing because I use high energy, small energy differences. What does high energies mean if your energy is bounded from above? So that's something we're working out at the moment. See Andreas as poster if you want to find out more. Okay, so now I've come to the second part of my talk, which is completely independent and completely different from the first part. It's a different model where I'm going to try to find quantum group structure, but now in 3D gravity. And the situation that I will be interested in is 3D Chern-Simons theory with group G on a space-time manifold that is an annulus times time, where the annulus is then my spatial slice, and I will be interested in cutting this annulus in two pieces on a spatial slice. So an annulus is a ring, and I want to cut that ring in the middle so that I have an inner ring and an outer ring. That's essentially the setup that I want to study. Now in Chern-Simons theory, Wilson lines are the objects to study, and here I've drawn, so the annulus, so the outer boundary is the outer black circle and the inner boundary is the inner black circle. The dashed line is where I want to cut my space, so purely the space, not space-time, purely the space into parts. And here I've drawn various Wilson line configurations that you might have in Chern-Simons theory, and you see that they intersect this entangling surface, or this cutting surface at various points. And in the right picture, I've cut explicitly my space in two parts, and I've only drawn the outer piece. And these red dots here are where the Wilson lines have been cut by this dashed curve. And these red dots would correspond then to local charges, Wilson line endpoints, that live on the cutting surface or on the entangling surface. And these are usually called edge states. So this is in what is usually called the extended Hilbert space formalism. You need to extend your Hilbert space of gauge theory if you want to cut it in pieces to allow local charges at the cutting surface or at the entangling surface. In this language, to allow Wilson line endpoints to exist. Now, what I've drawn here is usual factorization map, the usual way to cut the Hilbert space of Chern-Simons theory into pieces that people consider. And this yields, if you do the calculations, not surprisingly, a Wessel-Minowita model that lives on the entangling surface. So the Wessel-Minowita model is essentially the dynamical model that lives on this dashed circle here, and that gives dynamics to these red dots that appear here. So there are local charges that appear when you try to cut Chern-Simons theory. So you break topological invariance when you do that. The Wessel-Minowita model breaks topological invariance of the Chern-Simons theory. So that's the usual way you would imagine trying to cut Chern-Simons theory into parts. And then if you do that, and now you try to compute the entanglement entropy of between the two rings, so between the inner one and the outer one, and you compute this, this leads to an entanglement entropy that is divergent and that scales with the area of the entangling surface, or the length in this 2 + 1 dimensional case of the entangling surface. As usual, so due to the usual local short range entanglement you always have in QFT, in this case, this entanglement is just coming from the Wessel-Minowita degrees of freedom that are living at this entangling surface. So this is the usual story. Now the discussion that I want to start here is that this factorization and extended Hilbert space description, so this introduction of local charges, is inherently ambiguous. So as a silly example, you can always just add a qubit in an entangled Bell state on the entangling surface. This enlarges the extended Hilbert space because I have by hand introduced an extra degree of freedom at the entangling surface, and it also enlarges the entanglement entropy because these qubits are in an entangled state. It's clear, of course, that this is artificial, right? Because I've just added this by hand. But there is this ambiguity when extending your Hilbert space. How much should you extend your Hilbert space? So the question that I want to ask is, what is the minimal procedure to factorize a gauge theory? And it's clear that a minimum, in principle, should exist, since you should always be able to reglue the model by integrating over a complete set of edge states. Like the entire purpose of these edge states is such that you can reglue them in the end and recover your original space where you didn't cut it in two pieces. If you don't have enough edge states, then well, you cannot do that, and you just have two disconnected pieces of So as an example, a well-known example, if you consider 4D Maxwell theory, then these edge states, these extra degrees of freedom you have to introduce if you try to cut Maxwell theory into pieces. These are just surface charge density profiles that live on the entangling surface. And you need all possible surface charge density profiles, all rho of x, in a path integral context, or path integral over all of these, in order to be able to reglue the model, or in the language of Wilson lines that I'm using here, in order to be able to reproduce all two-sided Wilson lines, all Wilson lines that pierce the entangling surface. So they can pierce it everywhere, anywhere on the entangling surface, and they can have an arbitrary charge where they end. So in total, on that entangling surface, I need to allow for an arbitrary charge density profile there in order to be able to reproduce all possible Wilson lines that pierce the entangling surface. So I need all of them.
You can choose the presentation of the Wilson line, or they have to be.
Yes, but all of them can be there, so I have to allow for all of them. So I have to, in the Boolean case, I have to allow for all charges to be there. So that was the abelian case, but more generally, and well, the above considerations, they lead to a field that's living on the entangling surface, a surface current, if you want, and its conjugate, which I call h of x here, which is a large gauge degree of freedom that has become physical at the entangling surface. So large gauge degrees of freedom become ungauged and become physical at the entangling surface. And these two fields, so they're conjugate and they satisfy this algebra in general. So this is the answer for the non-abelian case, and this is a structure that is well known and has been studied for 10 years by now as the set of degrees of freedom that you expect to live at the entangling surface when you cut a non-abelian gauge. But Chern-Simons theory in particular, it additionally has topological invariance, which normal gauge theories do not have. And topological invariance allows us to deform Wilson lines on this angular spatial slice using the equations of motion. Now, if I just deform Wilson lines on this spatial slice, these are the same Wilson lines that I drew earlier, I just deformed them slightly, and I forced all of them to pierce the entangling surface at the exact same point. So I can just move these red dots around on the entangling surface using the fact that Chern-Simons theory is topological, and I can just deform the Wilson lines, which I cannot do in other gauge theories, like in Yang-Mills theory or Maxwell theory. What that suggests is that these edge state degrees of freedom, they can be reduced from a full field that's living on this entangling surface to a single charge or a single group element, H, that's living on the entangling surface. So I should be able to reduce them from field theory to just quantum mechanics if you want, just using the topological invariance of this model. And this is the story that I will try to work out now in technical detail. I will go relatively fast through this, so there's a lot of technical machinery we need here to write down the formulas that correspond to this story. But I'll try to illustrate the main points. And I will work classically for 90% of what I will say from now on. Now, the classical phase space algebra of Chern-Simons theory on the spatial annulus is spanned or is described just by the set of all Wilson lines that connect the two boundaries. So I've already drawn you various of these Wilson lines in the earlier pictures. So my notation here is W of x plus and x minus is a Wilson line, and x plus and x minus are two coordinates, spatial coordinates, that live on the inner and the outer circle. And just using the Chern-Simons action, so this is just a calculation, a technical calculation of Chern-Simons theory, you can write down the Poisson bracket of two of these Wilson lines. And that Poisson bracket is given by that expression, so there's a lot of notation in here. So K is of course the level of Chern-Simons theory, the K that appears in the action. And then I have this object W of x1, x2, and then two other ones. And what these objects all mean is as follows. So here I've drawn a piece of those two circles of my annulus, and I've drawn two arbitrary Wilson lines, and they might cross each other somewhere in the middle on this red dot here. And now if I decompose these Wilson lines, so each of these Wilson lines in three pieces, so I have these outer segments here that hit this cross here, and I call that, so for instance for this line, this is W x2 plus x2 minus, where the x2 plus coordinate lives here and the x2 minus coordinate lives there. The W of x2 plus is just this part of that Wilson line, and then here I have W minus 1 of x2 minus, and I do the same with the other Wilson lines. So I decompose these Wilson lines in all of the pieces, those are the ingredients that appear here. This epsilon that appears here is just an oriented intersection number, so it just counts, with sign how many times these Wilson lines intersect in the bulk. And then there's a whole bunch of notation that I've introduced here as well, and this is standard notation in the integrability literature. So I have these subscripts 1 and 2 here, these W's. What they mean here is these are parts of the tensor products of these two things. So the W's are matrices if you want, and now I take the tensor product of two of these, and then W1 is the thing that's hiding in the first tensor factor, and then W2 is the object that's hiding in the second tensor factor of the tensor product. So if you want, this thing here is a thing with 4 indices, and I take the IJKL, and then I take the IJ of the first one and the KL of the second one. So this is just some notation for the tensor product. That's what the 1 and 2's mean here, and then the C1, 2 here, that's what is called the tensor Casimir. It's the thing you get by taking the tensor product of the generators of the algebra, and then I put the inverse of the Cartan-Killing metric there. So a lot of technical notation. You don't have to remember a lot of this, but this is just the standard language one uses in the integrability. Okay, so that's just Chern-Simons for these two-sided Wilson lines. So Wilson lines that start one boundary of the annulus and go together. Now I want to actually do the story that I'm trying to say. I want to split space and also these Wilson lines in two pieces. So here in green I've drawn this Wilson line going between the two boundaries, and now I cut it. That's what I've drawn in blue here. I cut it along this red dot, and I replace it by these what I will call one-sided Wilson lines. So W of x plus and W minus of x minus on left and right of the cutting surface, left and right of the entangling surface. So this is what I'm writing down in formulas. Now this full phase space that I had earlier, if I want to describe this in terms of these blue lines, these one-sided Wilson lines, I can parameterize this full phase space now by this, or in this language, where again I just have all of these, so this is just a full two-sided Wilson line, but now parameterized in terms of these one-sided Wilson lines. But if I do that, if I use these one-sided Wilson lines, I have to allow for an extra degree of freedom, which is this monodromy that appears here. So if I go around the full annulus, so that's what this plus 2 pi means, like I move this x plus point all the way around the spatial annulus, I can pick up a monodromy, an arbitrary monodromy, and that's what this m plus minus here means. Another way to say that is that these one-sided Wilson lines, if you want, these W of x plus x minus, they're not single-valued functions on the annulus. Another way to see that is that with these one-sided Wilson lines, they're actually just the normal G you would have if you write a flat gauge connection. A mu is dg times G minus 1. That G doesn't have to be single-valued on your space-time, and that's exactly what I'm doing here. This is also familiar if you're familiar with the phase space description of chiral WCW models. Okay, so now I'm interested in these, what I call one-sided Wilson lines, and they satisfy this bracket relation with the Gasmoudi current that's living on these inner and outer boundaries. So the inner and the outer boundary of my annulus, those are actual boundaries, that's where I have WCW models living. Not at the entangling surface necessarily, that's what I'm trying to figure out what's living there, but at the inner and outer boundaries I have Gasmoudi currents. And this is just a textbook relation. This Gasmoudi current has a Poisson bracket with these W's given by this. If you want, this is just a relation you find in the CFT textbook of the current with the group element G. This is the same relation. So it's given by this type of relation. Now, what I'm interested in here is that this J, the Gasmoudi current, is just the W times W minus 1. Plug that in, and now I want to integrate this to get the WW bracket. So I have the bracket of essentially the derivative of W, and I want the bracket of W itself. So you can, work with this equation a little bit. I write this as a first order differential equation for the WW bracket. Then you integrate, and then you get this equation in blue here. And this is the most important equation, or the equation that leads to all of the structure that I want to discuss. So you get this Poisson bracket of two of these one-sided Wilson lines in this way. Now, because I got this by integrating a differential equation, I pick up an integration constant that I call R12 of x12. So again, a little bit of notation here. So what do I mean by that? This object here is, so it's a function of x12, by which I mean x1 minus x2, so the difference between the two x's. And it's given just by something that is independent of these x's, and then plus or minus a half times this Casimir tensor operator we had earlier. And then the dependence on x1 minus x2 is just in the sign. If x1 minus x2 is bigger than 0, I pick the plus sign. If x1 minus x2 is less than 2, I pick the minus sign, and that's it. So it has a very weak dependence on these x1 and x2 coordinates that we have here. It just depends on the sign, which one of them is bigger than the other, and that's it. And this R12 is literally just a constant, an integration constant when you integrate this differential equation to get this thing. So it's x independent. And it's a matrix. It's called R12. And you can immediately see that it needs to be antisymmetric. R12 needs to be minus R21. And if you want this bracket to satisfy the Jacobi identity, you get another constraint on it, which you can write in this way. And this is a famous equation, again, in integrability. This is called the modified classical Yang-Baxter equation. So the logic here is that to try to find the WW bracket, we integrated another, we integrated this relation. We pick up an integration constant. That is, of course, undetermined from the structure that we had up to this point. But it is constrained by consistency. It needs to be a solution of the modified classical Yang-Baxter equation. So we find this integrability structure in Chern-Simons theory for the WW brackets. Let me skip this for now. Okay, so with this WW bracket here, we can now compute three brackets that I'm mainly interested in for the purposes of this talk. One of them is the bracket of these monodromies. So these monodromies, the monodromies were picked up as I circle the annulus. Then I pick up this monodromy matrix. The W's are not single valued on the annulus. And these monodromies are then fully determined, of course, in terms of the W's themselves. You pick them up as you go one circle around. And you can just compute the bracket because I know the WW bracket, and it's given by this complicated looking expression, but this is a structurally very nice expression. This is called the Semyonov-Tyershansky bracket. Very well known bracket in classical integrability. And then finally, I'm going to split up my W of x. So these were at this point these blue Wilson lines, these one-sided Wilson lines. I'm now going to split them up as g of x times h, where g of x is now really the boundary WW field that's living on the outer boundary, and h is the degree of freedom that's living on the entangling surface, and that doesn't depend on x. So here I'm just using my physical assumption here that there's this large gauge degree of freedom here that's become physical on the entangling surface, and it doesn't depend on x. It's just a quantum mechanical degree of freedom. It's not a field anymore. So here I'm implementing this in my formalism. And if I split my W in these two parts, then I can just get induced from that another bracket of this large gauge transformation at the entangling surface, the HH Poisson bracket. And this also is a well-known bracket in integrability. It's called the Skleanin bracket. And then finally, you can see how the M and the H variables talk to each other, and you find again non-trivial bracket from that. So in total, you find a set of three Poisson brackets. One of them describing how the monodromies talk to each other, one of them describing how the large gauge transformation at the entangling surface talks to itself, and the last one how these two things talk to each other. So if we summarize, this is the total Poisson algebra we get living at the entangling surface. And it's fully parametrized, or it's fully known, if I give you this R12 matrix. And this R12 matrix, it was constrained, and it has to be an antisymmetric solution of the modified classical Yang-Baxter equation. So that is the structure that we have found, the phase space structure that is living at the entangling surface of Chern-Simons theory, if we try to impose that we have this minimal factorization instead of the domiciliary factorization. So these are the degrees of freedom. These are the edge degrees of freedom that are living at the entangling surface. Now all these brackets have names, so of course this is a known structure, and this is sometimes called the symplectic or the Heisenberg double in the literature. And as I mentioned, it provides a phase space description of the edge states. This is a phase space algebra of a particle on a quantum group with a coordinate h and a momentum m. This is not yet a full quantum group because these are just Poisson brackets, they're not commutators. But this is the classical structure that is underlying quantum groups. So if I would quantize this, replacing Poisson brackets by commutators, then I would get actual quantum group structures living at the entangling surface. And I want to compare this algebra to the algebra that I started with in this part of the talk. So I mentioned that there was this Poisson bracket algebra of surface currents and large gauge transformations. This is that algebra again, so I've written it, instead of current densities, I've written it in terms of the total charge living at the entangling surface. So this was the story we had in the beginning. And you should compare this algebra here to this algebra. So the algebra that we arrived at now is a non-linear generalization of the previous linear algebra that one argues in general you would have at entangling surfaces in gauge theories. And that would lead to WCW factorization. Now, here I've found this non-linear version, but it's not a field, it's just a quantum mechanical degree of freedom at the entangling surface. But it's non-linear. That's the price you have to pay. Now, this non-linear structure at the entangling surface, parts of this structure have been found earlier, and this was also part of our inspiration in early literature from the early 90s, when people looked at how to factorize the non-chiral WCW model into its two chiral parts, and this is a non-trivial thing to try to do. And this algebra has also been proposed in the past, perhaps somewhat ad hoc in my opinion, in what is called combinatorial quantization of Chern-Simons theory, where people consider discretizing a closed spatial manifold, and then imposed these brackets that are called Fock-Roselik brackets for Wilson lines along the edges of this discretized spatial manifold. So, well, there is literature here that explores various aspects of this. That's what I wanted to say here. Okay, so I mentioned, so we found this nonlinear algebra now. And the structure of this algebra, of course, depends on the R matrix. I need to give it to you. I need to tell you what this R matrix is, and then you can see what the exact phase-space algebra is of these edge modes. So it depends on this. And it was only constrained by being antisymmetric and solving the modified classical Yang-Baxter equations. Now, if I take that R matrix, and I go to this R plus minus here, which, well, is notation that I introduced earlier, you can readily see that that one just needs to solve the ordinary classical Yang-Baxter equation, not the modified one, so that's just this type of thing. And there is a classification of solutions of this classical Yang-Baxter equations for simple Lie algebras due to Bellarmine and Drimfeld. So these solutions have been classified. So you can, I mean, it's not just that you can do whatever you, it's not that there's an infinity of possibilities here. There's a classification of possible R matrices. And in particular, you can find real solutions for complex algebras such as SL2C and the maximally non-compact real form like SL2R. But for instance, SU2, the compact real form, doesn't have real solutions. So this might sound like a technicality, but the R matrix appears at the right-hand side of Poisson brackets, and I prefer those things to be real if I want an ordinary real phase space. So I'm interested in real R matrices. So that means if I'm interested in real R matrices, I can actually only do this for SL2C, for instance, SL2R, but not really for SU2. So this is a complication. I will be interested mostly in SL2R though, because of gravity. So that's the example that I want to work out now. So I want to show you some formulas to make all of this abstract discussion a little bit more concrete, to show you how you actually work with these things. So for the specific case of SL2R, there's a unique solution that is called the standard R matrix. And here I've written it down just as the fundamental 2x2 representation. So the R matrix is living in the tensor product, so that makes it a 4x4 matrix. And this is what they look like. So these are very simple matrices. Given that R matrix now, you can just work out all of these brackets and see what they mean. So the first one is this Kleanin bracket, which look like that. So the H matrix that appears here is an SL2R matrix. So I parameterize it as A, B, C, D with AD minus BC is 1. And then on the left-hand side, this Poisson bracket of H1 and H2. So remember, the 1 and 2 means in which tensor factor this object is living. So the left-hand side is just this matrix of Poisson brackets of all of these possibilities of A, B, C, D with A, B, C, D. And then on the right hand side, I just compute this commutator of H1, H2 with the R matrix that I had on the previous slide. So this is just simple 4x4 matrix multiplication that I'm doing here. And you find this matrix of right hand size. Now you can just read off what the different entries are, and then you find this Poisson algebra satisfied with of the 4 entries of the H matrix, the A, B, C, Ds. You find this type of algebra. Now this type of Poisson algebra, you can recognize this as an H bar to 0 limit of the quantum group SLQ2R again. So if you look at the literature, the quantum group SLQ2R is an algebra that's spanned by A, B, C, D, which are non-commuting, and they satisfy in particular those types of relations. So AB is not BA, but there's a price of Q, Q to the half that you pay if you try to swap them. So that's the definition of SLQ2R. If you take these relations and you take the H bar to 0 limit, where you, of course, you go from commutators, you go back to Poisson brackets, then you find this Poisson bracket algebra. So that's the structure that we have here. So it's indeed just the classical limit, the H bar to 0 limit, of the known mathematical SLQ2R quantum group. You can play the same game for the other brackets now. So this is one of the other brackets, the Semenoff-Janshansky bracket. Just plug in your R matrices, multiply 4x4 matrices together, and you get this bracket. Again, a convenient way to parameterize your M matrix. So I parameterize my H matrix as A, B, C, D. It's convenient to parameterize my M matrix in this way. This is also a good parameterization of an SL2R matrix in terms of objects that I call K, E plus, and E minus. You plug them in here, this parameterization, and you find these types of brackets between K, E plus, K, E minus, and E plus, E minus. And this again can be viewed as the H bar to 0 limit of the quantum deformed algebra. So here I've written the quantum deformed algebra. Taking H bar to 0 and replacing commutators by Poisson brackets, you find the structure again. And then you can do the last bracket as well, but it's not super interesting. So maybe one comment that I should make here at this point. I haven't really specified this or emphasized this, but when I say the H bar to 0 limit, so we take a full quantum group and in the H bar to 0 limit we get these Poisson brackets, I want to emphasize that this is very different from the Q to 1 limit. The Q to 1 limit is the limit where all of this nonlinear structure, this quantum group structure, linearizes again, and you go, for instance, from quantum group to a Lie group. But this is different from H bar to 0, where you go from commutators to Poisson brackets. So you need to distinguish between H bar to 0, the physical H bar to 0, the way in physics we quantize a system, and the mathematical Q deformation of linear structures into nonlinear structures. So that's a comment. Let me skip these things and get to the final part. Because my original interest in doing that was actually to talk about 3D gravity, and I haven't even mentioned 3D gravity at all. I've just tried to describe a way to factorize Chern-Simons theories in general in a minimal way, in a way that is not with the WCW model living on the entangling surface. So what does all of this story now, what does all of this imply for the actual 3D gravity case? Now, if I consider the von Neumann entropy, the entanglement entropy in 3D Chern-Simons theory, and I consider a state that has a Wilson line and a representation R that crosses the entangling surface, if I would use the WCW factorization map, and I argued that, or I try to, my entire story has been to try to find a different factorization map, but now let's see if we take the usual one, the WCW factorization map, what do we get? If I do that for Chern-Simons theory, I get an entanglement entropy that looks like this. So I already discussed this L over epsilon term, this usual short-range entanglement term you always have. But there's some additional terms. So one of these is log of the quantum dimension of the representation of the Wilson line that crosses the entangling surface. So this is the usual entanglement entropy you can compute in Chern-Simons theory. And I want to focus on these first terms. So these first terms are the vacuum entanglement entropy. You get them if you put R equal to the identity. And in particular, I want to look at this divergent term again, this area term, this L over epsilon term you always have when you try to factorize field theoretic systems. So it's proportional to the length of the entangling surface. But this is, well, in the Chern-Simons formulation, so Chern-Simons theory doesn't depend on a choice of metric, it's topological. But here you have a length appearing. So this actually appears here because you break topological invariance at the WCW boundary in Chern-Simons theory. So this actually appears from a background metric you introduce by hand at your boundary. So that's an important comment. And then secondly is that it scales as 1 over epsilon. It's divergent, of course, and this is actually coming from the fact that the WCW model at the boundary, for each primary there's an infinite number of descendants. And you're essentially counting all of the descendants per primary, and there are an infinite number of them, and that's where you can track this 1 over epsilon to, in this case. So these are just some comments about if you try to factorize Chern-Simons theory with the WCW map, what it looks like. And then this last term is actually an interesting one. This is called the anion defect entropy or topological entanglement. Okay, so the main question that I want to ask for the second part of this talk was, can we use this WCW factorization map to factorize 3D gravity? My answer will be no, because otherwise I've introduced all of this minimal factorization map stuff for no reason. But let's entertain this possibility. Can we apply the WCW factorization map to 3D gravity? So 3D gravity in its first order formulation for negative cosmological constant is just described by 2 copies of SL2R Chern-Simons theory, where these 2 gauge connections, A and A bar, they encode the Vielbein and spin connection in this gravity in this known way. And now, if I try to interpret this type of formula in a gravity language, the first term just looks like a Bekenstein-Hawking type of term. So in A over 4G, but I have A over epsilon, so I just renormalize Newton's constant and so on. So this is the usual interpretation you would give if you're doing QFT in curved space-time to that type of term. But there is a conceptual problem with trying to interpret this L over epsilon term in the same way as you would do in QFT in curved space-time. Because the physical metric used to measure lengths, the actual length, in 3D graph is encoded in A and A bar, whereas this length here was just introduced by hand when you break topological invariance of Chern-Simons theory. This is a very different metric than the actual metric. The actual metric is encoded in the values of the fields, because if I give you A and A bar, I give you the Vielbein and spin connection, and you get the metric, and then you get the geometry. It's very different from where this L actually comes from in Chern-Simons theory. So there's a discrepancy here. And this suggests, or this implies, that this term actually has nothing to do with the actual black hole area. It shouldn't be interpreted as something that is A over epsilon that just renormalizes Newton's constant, because the A is very different from the actual A would have in gravity. So there's a big conceptual problem here if you try to apply that usual trick to gravity itself in this Chern-Simons formulation. So this does not work. You cannot just use this formula and apply it to 3D gravity. It makes no sense. Now, a solution would be if we didn't have this term, if we didn't have these first terms. Now you can remove precisely these terms if you can remove descendants at the entangling surface, which means you actually reduce from WCW model factorization. If you drop all of this descendants, you just get the primaries again. This is essentially reducing from the full WCW model back to the particle and group. I should wrap up?
Slowly.
Yes. Okay, I'll go fast. And it would lead to the entangling entropy to be just that anion defect entropy, and that's exactly what this minimal factorization map is doing for us. It's killing all of the descendants you would have. It's reducing WCW down to the zero mode sector, but the zero mode sector is nonlinear, it's Q-deformed, and that's exactly what this formula is doing for you. So let me. Well, now you need to specify more complete. So this log of the quantum dimension, I need to tell you what the representation itself actually is. So the group structure is SL2R or SLQ2R. And then you need to pick the correct representations, which are these principal series representations. You plug in the correct value for this quantum dimension, and you can show, if you're, for instance, in the semi-classical regime of it, you just reproduce the BTC black hole entropy. So you just reproduce the BTC black hole entropy as an entanglement entropy using this minimal factorization map. So that's the main conclusion. So if you want, you can say that the gravitational entanglement entropy, BTC black hole entropy, can be interpreted as an anion defect entropy or as a topological entanglement entropy. And that's what this way of factorizing Chern-Simons theory has done for you.
Sorry, this dependence on the representation has disappeared or
No, it has, or it hasn't. So the choice of well, I skipped through this, but the choice of representation. So I need to pick two representations because I have two chiral sectors, and this choice of representation is one-to-one with the mass and the angular momentum of the BTC black hole. So I give you the mass and the angular momentum of the BTC black hole. That's equivalent to giving you these representations, and giving the mass and the angular momentum gives you the area, just using the classical format. Okay, so let me conclude. So my talk consisted of two parts. The first part, I discussed the emergence of quantum group symmetries in 2D gravity. I discussed purely from the symmetry perspective how a two-point function looks like in this Q-deformed setting, and particularly this quantum hyperbolic disk geometry. And I found it in particular as a limit from some dynamical model, the Liouville gravity. The second part of my talk was about 3D gravity, and I constructed purely in Chern-Simons theory a different way to cut the Hilbert space in two pieces, where you don't have the full WCW model living at the entangling surface, but just the zero-mode sector, just a particle on a quantum group that's living there. And I argued that you have to use this factorization map if you want to understand how to factorize the Hilbert space in 3D gravity. And this then led to the statement that you can interpret the BTC black hole entropy as a topological entanglement entropy. Okay, thank you.
Any more questions for Thomas?
Yeah, I'm a bit confused about the role of H bar. I know you explained it, but so this SFTQ arises because you are doing quantum Chern-Simons or
Yes. So, well, I had this slide where I wanted to make a distinction between the difference between Q to 1 and H bar to 0, right? So the comment that I made there was, like if you open math books, for instance, on quantum groups, they would start with saying like, here's a Lie algebra, and now you Q deform that to get to or you non-linearize it to get to a quantum algebra. All of these are quantum from the physics perspective. If you want to physically quantize a system, you have to start with Poisson brackets and then replace it by commutators. So these are like two perspectives to get to quantum group structure. And that's why I had this picture where I have these four theories with the limits in between. So if you want, you can physically quantize, which is what we ordinarily do with dynamical systems, replacing Poisson brackets by commutators, or you can mathematically quantize, which is just nonlinear deformation of Lie algebras and Lie groups. That was a comment.
okay?
I'm not sure if this is
you
right.
found this deformation, which is just the first order deformation of the full SFTQ, right?
What do you mean by first order?
So you have only the linear the quadratic part.
Oh, because we do Poisson brackets. You mean?
No. This bracket that you showed, like, has terms like AB, commutator AB is AB,
Yes.
and you say that's the H bar zero limit of the full thing.
Yes, like these types of.
Yeah, exactly.
Yeah, so these are the exact answers. If you take the full quantum group, the SLQ2R coordinates of the algebra.
But you didn't find that, you just find...
If I take H bar to 0 and pick the leading term, I get this. If I would quantize this, I get here. But of course, quantization is in general not unique, right? So these are the two structures.
Just by replacing this Poisson with the commutators, and still keep only the...
Yes, in the H bar to 0 limit though. So the statement is you take H bar to 0 of this thing, and then you replace commutators by Poisson brackets, and then you get back to this thing.
So in the full quantum theory, I should think that this...
There could be higher order corrections in H bar squared and so on that appear here that you don't see here, of course. This is the ambiguity in general in quantization. But this quantizing this algebra in this way is structurally the most natural one because you preserve, you get a lot of structure. You get this full coordinate of algebra emerging there.
Maybe I have a very question. Like, I thought that there were some problems in actually identifying the quantum gravity but integral with the Charles-Simons but integral?
Well, there's a lot of subtleties there, definitely.
it's
So
just
here
a-
I'm really working in this first order formulation, so the group theoretical framework for 3D gravity. There's lots of subtleties in when this actually works for full gravity. Higher topologies, for instance, can be subtle. This is the analog of in 2D, these Mirzakhani relations and so on, or global diffeomorphisms that
I thought it
game
was
theory
for
doesn't take
example.
into account. So there's like this whole list of subtleties, but these are understood in principle. So we know when the group theoretical or the first order formulation of 3D gravity works and when it doesn't.
Yes,
My entire story is about factorization as in principle a local statement. So I just take a complicated three-dimensional manifold. Here I only work with annulus times time because that's, let's say, the annulus is the standard structure you would take to cut in two pieces. But you can apply this to more complicated geometries, and this is a local statement there, so it should still hold.
Okay.
I mean, I'm only describing the local Hilbert space you get if you cut at a specific location.
But don't you have, for example, the issue that you're integrating over the generic matrix?
Yes, but okay, so that's another thing. So these, so this is related. Well, these are some slides that I actually skipped in the end. If you want to identify gravity with gauge theory, you always say or read SO2R, but it's a bit more subtle than that. And the cleanest way is if you think about the moduli space of flat SO2R connections. This has several components, and one of them is called the Teichmüller component, and that's the one you should take. Taking that one solves this issue of non-degenerate metrics. So you can phrase this as a subtlety in picking the correct group theoretical structure that is underlying 3D gravity. And the thing you have to pick is called this modular double of SOQ2R. That's the group theoretical structure you have to take for 3D gravity.
Okay.
But this is a long discussion.
Yeah, yeah, yeah.